Hi everyone, welcome back. In this lecture we're going to look at how to differentiate the composition of functions. And just as a reminder, if we have two functions f and g, we can define their composition denoted by f and then this little circle g, so f circ g, or f composed with g, by first evaluating at your input x the function g and then following that by evaluation at f. So first apply g, and then whatever comes out, then apply f, and that result is known as the composition of f with g. So notice the composition of f with g, you sort of read it from the inside or from the right to the left. This is the first function that's being applied to your input. This is the second function that gets applied to whatever came out of the first function. So let's look at a quick example. If f is the function f of u equals sine u, and g is this second degree polynomial, then what is their composition? Well, their composition is f composed with g at x. It's first evaluate the input at g, the inside function in this case, which is g, so that's a 1 plus x squared, and then take that result and evaluate the function f there. So f is the sine function, so this would be sine of 1 plus x squared. Okay, and so there's our result. What we call, and this will be helpful in what we're going to do next, what we're going to call g is we're going to call it the inside function. It's really the first thing that's getting applied. And then we're going to call f the outside function. It's sort of the function that's just waiting on the outside for whatever came out of the first function that was applied before you can evaluate it. And I'm going to use these terms inside and outside when we start to talk about the chain rule. Okay, so here's the statement of the chain rule. If you have two differentiable functions, f and g, and you look at their composition, which we'll call big F, defined to be first apply g and then apply f of that, so the composition is f composed with g, then the derivative of big F is obtained by first taking the derivative of the outside function and evaluating it at the inside function, and then multiplying that by the derivative of the inside function. So to compute the derivative of the composition, you take the individual derivatives of the pieces, the inside and the outside functions, and you put them together in this way. Derivative of the outside evaluated at the inside, and then times the derivative of the inside function. In Leibniz notation, if y is a function of u and u is a function of x, and the functions are differentiable in this case, then the derivative of y with respect to x is again the derivative of the outside function, but using Leibniz notation, it's dy by du times the derivative of the inside function, which is du by dx. So when we think of the chain rule, we're going to think about it verbally, and you'll hear me say this over and over again as we start to do examples. The derivative of the composition is the derivative of the outside function evaluated at the inside times the derivative of the inside function. So that's going to be our mantra. We'll repeat that over and over again as we do these examples. So right now we're just going to look at a whole bunch of examples and get some practice with applying the chain rule. So in this first example, we have f of u is sine of u and g of x is 1 plus x squared, and we're going to look at what the derivative of the composition of f with g is. We're going to need to know the individual derivatives. So the derivative of f is the derivative of sine, which is cosine of u in this case, and the derivative of g is 2x. Now having those, we can compute the derivative of the composition. The composition, which was f composed of g at x, its derivative is the derivative of the outside function evaluated at the inside function times the derivative of the inside function. Now, the derivative of the outside function, that was the cosine. So that's cosine evaluated at the inside times the derivative of the inside function. So here we have that the inside function is 1 plus x squared. And we're going to need to then multiply by the derivative of the inside function, which is 2x. So our result is 2x cosine of 1 plus x squared. Okay. So again, we need to know the derivatives of the individual pieces, derivative of sine and the derivative of this polynomial. And once we have those, the chain rule tells us how to reassemble those to get the derivative of the composition. Let's look at the next example. We're looking at y prime, which is the derivative of 2 minus 5x cubed. So the chain rule tells us that this is going to be the derivative of the outside function. Okay, now we need to identify what the outside function is. What's the last thing that's being done here? It's a composition. So if I think of trying to evaluate this function at some particular x value, the first thing I'm going to do is take 2 minus 5 times that value. So that's my inside function. The last thing I do is I cube it. So that's my outside function. So the cubing function is the outside function. The derivative of the cubing function would be 3 times whatever was inside squared. And then I need to multiply by the derivative of the inside function. This is the chain rule. So this was by the chain rule. Now what is our inside function in this case? Well, that, as I mentioned, was 2 minus 5x. So that's what the chain rule tells us. You need to know the derivative of the outside function, which we've written down, but you also need to know the derivative of the inside function, which we can now work out. So this would be 3 times 2 minus 5x all squared. Derivative of the inside function, now we're looking at the derivative of this linear function, which is negative 5. And so this becomes negative 15, 2 minus 5x all squared. Okay, so let's try a few more examples to get the hang of this. We're going to work out the derivative of this, y prime, which is the derivative of x plus sine of x to the fifth times 1 plus e to the x all squared. So do we apply the chain rule? Well, I mean, we need to be careful here. We have to think about how this function is built up. At the very top level, what's happening here? What operation? Is there a composition or is it something else? So how do you figure this out? Just imagine evaluating this function at x. The first thing you would do is probably take x plus sine of x, work out what that is, and then you take the fifth power of that. But then you'd also work out what 1 plus e to the x is, and then square that. And then the final thing you would do is take their product. So at the topmost level, this function is built up as a product of two other functions. The two other functions are this x plus sine of x to the fifth and 1 plus e to the x squared. So right in here we have a product. So if our function is built up as a product of two other functions, the very first thing we do when taking its derivative is apply the product rule. So let's apply the product rule then. So it's the first function times the derivative of the second, 1 plus e to the x all squared. And then we add to that the second function times the derivative of the first function, x plus sine of x to the fifth power. Now this was by the product rule. Now at this stage, we scan through and say, are there any derivatives we need to evaluate still? And sure, there are a couple of derivatives. There's this derivative of 1 plus e to the x all squared and another derivative of x plus sine of x to the fifth. How are those ones built up? Well, this first one is a composition. There's this inside function, 1 plus e to the x, and it's being squared. So here is where the chain rule would be used. So let's go to work on this. It's x plus sine of x to the fifth power times, now we go to work on this piece here, and that's the chain rule. So it's going to be the derivative of the outside function. What's the outside function here? What's the very last thing that's being done when you imagine evaluating at a particular x value? It's 1 plus e to the x, and then you're squaring that. So the squaring function is the outside one, so that's going to be 2 times the inside function times the derivative of the inside function. The inside function in this case is 1 plus e to the x. And so that's the chain rule now being applied. And we can do the same thing for the next term. X plus sine of x to the 5th power. It's the derivative of the outside function. The outside function is the power function, the 5th power function in this case. So it would be 5 times whatever was inside to the 4th power. So that's, maybe I'll change colors like I had before. That's our x plus sine of x. And then we need to multiply by the derivative of the inside function. And that is our x plus sine of x. So we've now broken this stuff all the way down to now just having to evaluate these two derivatives. And each of these is a sum of functions, so we can use the fact that the derivative of a sum is the sum of the derivatives. So this first one becomes an x plus sine of x to the 5th times 2, 1 plus e to the x, times the derivative of 1 plus e to the x. That's just the derivative of 1, which is 0, times the derivative of the e to the x, which is just e to the x, plus this other term, 1 plus e to the x all squared, times 5, times x plus sine of x to the 4th, times the derivative of x plus sine of x, which is 1 plus cos of x. Okay. Now I probably should have written here that this previous step was by the chain rule, just to be consistent with what I've done above, quoting the product rule when I use it. Now I've used the chain rule. This last step, of course, was just differentiating a couple of elementary functions. So now we've got our derivative. There's some common factors, and we could probably pull those out. I notice that I've got an x plus sine of x to the 4th power in common, and 1 plus e to the x to a single power. So I have an x plus sine of x to the 4th. A 1 plus e to the x can come out of each term. And what does that leave me with? Well, in the first term, I'm left with a 2 e to the x, 1 plus, x plus sine of x, x plus sine of x. And in the second term, I'm left with a 5. I'm left with a 1 plus cos of x, and I'm left with a 1 plus e to the x. And so there is our derivative. So this shows that taking a derivative may involve the application of more than one of these rules. We needed to do a product rule here first because it was a product of two functions. The individual factors were then compositions, so we had to use the chain rule. And then those pieces were sums, so we had to use the sum rule for differentiation. So we may need to involve more than one of the rules. In fact, in most cases, we will need to involve more than one of the rules. Okay, so let's look at another example. Let's express the derivative dy by dx in terms of x. So here we're just getting a little bit of practice in Leibniz notation. We've got two functions here. We've got y is a function of u, and then u is ultimately a function of x. So this means that y can be written as a function of x. Since I can write the inside function here, which is u, as this rational function, then computing y would just be taking this thing and raising it to the 5th power. So there's a composition here. In Leibniz notation, the derivative dy by dx is, well, y was a function of u, so we need to know the derivative of the outside function with respect to the inside. And then we need to multiply by the derivative of the inside function with respect to its variable. What's dy by du? Well, that's going to be 5u to the 4th. And then we need to multiply by du by dx. So that's going to be the derivative of 4x minus 1 all squared all over x. Now that's going to involve the quotient rule. So this is 5u to the 4th. What does the quotient rule tell us? Well, it tells us it's the bottom times the derivative of the top. 4x minus 1 squared, minus the top, 4x minus 1 all squared, times the derivative of the bottom. But the derivative of the bottom in this case is just 1. And all that's over the bottom squared. And so this is then 5u to the 4th x times the derivative of the top. Well, the top is a composition. It was 4x minus 1 all squared, so we need to apply a chain rule there. It's 2 times the inside function times the derivative of the inside function. And in this case, the inside function was 4x minus 1. And then we can carry on, and then that was minus 4x minus 1 all squared, and all that was over x squared. So that step was by the chain rule. And at this stage, now we just have one derivative left to calculate, or to compute, and that derivative is a derivative of a linear function. So we can get that easy enough. It's going to be 2 times 4x minus 1. Derivative of the linear function, that's just 4. And then there was this 4x minus 1 all squared, all over x squared. Okay. Now we're asked to express it in terms of x, the final result in terms of x. So we need to get rid of this u in place of what it is in terms of x. It's 4x minus 1 all squared, all over x to the 4th. And now we need to simplify this expression if we can. We have an 8 here, and that was multiplied by the x out front, so it's an 8x times 4x minus 1. And then we have this other 4x minus 1 all squared, and all of that is over x squared. And we can simplify this a little bit more. We have a factor of 4x minus 1 squared and then raised to the 4th power, so that's to the 8th power. But then we can also factor one of the 4x minus 1s out of these two terms, so that should be to the 9th power. And then what's left in here is an 8x minus a 4x minus 1, and all of that is over an x squared, but this one was all over an x to the 4th. And so simplifying a bit further, we get that this is 5 times 4x minus 1 to the 9th, 8x minus 4, that's a 4x, and now we have a plus 1, all over x to the 6th. And so there's our final result for the derivative. Okay, so let's have a look at a few more examples. What is the derivative of this function, square root of 2 plus 5x squared? Well, it's a composition. Outside function is a square root, inside function is this degree 2 polynomial. So what we're going to do first is just quickly rewrite it as a power so that we can use the power rule to differentiate the outside function. And here the derivative of the outside is going to be 1/2 2 plus 5x all squared to the negative 1/2. And then we need to multiply by the derivative of the inside function. So that's going to be the derivative of 2 plus 5x squared. So that's by the chain rule. And so this is then 1 over the square root of 2 plus 5x squared. The derivative of the inside function, which is this second degree polynomial. Derivative of 2 is 0. Derivative of 5x squared is 10x. And so the result is 10x. Oops, I forgot the factor of a 2 here. And that's going to allow us to cancel with part of the 10 to leave us with just a 5x on top. So 5x over square root of 2 plus 5x squared. And so there is our derivative. Let's have a look at this next example. It's tan of x squared all cubed. So here it takes a little bit just to see what's being composed? Well, there's a couple of functions. Actually, there seems to be three functions. There's this x squared, there's this tangent function, and then there's this cubing function. And I have to decide which one is the outermost function. Now, when we're applying the chain rule, things can get kind of messy if you try to look for too much going on. Right now, we're just looking at the top level. What's the very last thing that gets done? The very last thing that gets done, if you were to evaluate this function at a particular x value, the very last thing that gets done is the cubing. So that means that when I want to take the derivative, I just need to know the derivative of the outside function, which is the cubing function. And whatever the inside function is, no matter how complicated, no matter what it is, I'm just going to fill in these two blanks with it. So it's the tangent of x squared. Okay, so now we've reduced our computation of the derivative in some sense by one level. We've stripped off the outside function and dealt with it. Now we're left with trying to figure out what the derivative of the inside function is, and that is, okay, the derivative of tan x squared. That again is a composition. The outside function here is the tangent function. The inside function is the square. So we're going to have to apply the chain rule again. So this was 3 times tan squared x squared. Of course, this is just shorthand notation. Tan squared of the argument is equivalent to having the square on the outside. This is just shorthand notation that we've adopted for trig functions and their powers. This next one, the derivative of tan x squared, well, the derivative of the outside function, the derivative of the tangent, is secant squared. We're going to evaluate that at the inside function. That's the x squared. Then we're going to multiply by the derivative of the inside function. And again, we've now stripped off one more level. We stripped off taking the derivative of that outside function tangent, and we're now focused on the derivative of that innermost function, which is the squaring function. And now we can put it all together. We've got a 3 tan squared x squared, a secant squared x squared. The derivative of x squared is 2x. So I'll just pull that out front. Joined with the 3 is a 6x. And there is our derivative. So two applications of the chain rule. We had a chain rule here, and we had another chain rule here. Two applications of the chain rule because this was a composition of three functions. Okay, let's have a look at the last example. F of x is e to the cos x. Again, what's the last thing that gets done? Well, if I start with an x value, I have to evaluate cosine of that, and then I have to take the exponential. So the exponential is the very last thing that gets done. So in order to take the derivative, I take the derivative of that outside function, which is the exponential. The derivative of the exponential is itself. So the derivative of the outside evaluated at the inside is that, times the derivative of the inside function. And so this becomes then, the derivative of the inside is negative sine times e to the cos of x. And so there's our resulting derivative. Okay, so if you've had any issues with applying the chain rule, maybe go back and revisit some of these examples again, make sure you can do them and understand where the chain rule comes in and how we're applying it. Now we're going to look at another example, a much more general example, and then we'll do a few applications involving the chain rule.